For decades, we have been told that optimal health requires consuming 8 glasses of plain water every single day. But what if this deeply ingrained rule is fundamentally flawed? What if aggressively drinking pure water could actually leave your cells starving for hydration? Today, we peel back the layers of this pervasive myth, revealing the complex scientific mechanisms that govern how our bodies truly absorb and utilize fluids. We are going to explore the profound truths of cellular hydration, a process that extends far beyond the simplistic idea of just pouring liquid down your throat. By examining the intricate dance of minerals within our bodies, we will equip you with a nuanced understanding of how to genuinely fuel your biological systems. Let us understand the evidence-based science of what actually happens at the microscopic level when we take a drink. To comprehend hydration, we must first understand the microscopic architects of life known as electrolytes. In the realm of chemistry, an electrolyte is a mineral that, when dissolved in a fluid like blood or intracellular plasma, separates into positively or negatively charged ions. These charged particles are not merely passive building blocks. They are the essential conductors of the electrical currents that make human life possible. Every thought that races through your brain, every beat of your heart, and every contraction of your muscles relies on the rapid movement of these charged ions across cell membranes. Without them, the electrical signaling in our nervous system simply fails. The primary electrolytes orchestrating this symphony include sodium, potassium, magnesium, calcium, and chloride. When we talk about achieving true electrolyte balance, we are referring to the precise, homeostatic regulation of these ions in the fluids both inside and outside of our cells. It is this delicate equilibrium, not the sheer volume of water consumed, that dictates our physiological function. Let us delve into the actual mechanics of how water enters a cell. This brings us to a fundamental biological principle known as osmosis. Osmosis is the movement of water across a semi-permeable membrane from an area of low solute concentration to an area of high solute concentration. In simpler terms, water follows salt. If you have a high concentration of electrolytes outside a cell and a low concentration inside, water will rush out of the cell to dilute the exterior fluid, causing the cell to shrink. Conversely, if the interior is highly concentrated with electrolytes while the exterior is diluted, water floods into the cell, which can cause it to swell and potentially burst. True cellular hydration is the careful management of this osmotic pressure. It is about ensuring that the fluid outside our cells, the extracellular fluid, and the fluid inside our cells, the intracellular fluid, maintain a perfectly calibrated ratio of water to electrolytes. If you consume massive quantities of plain water without the necessary minerals, you dilute the extracellular fluid. Your body, sensing this dangerous drop in sodium concentration, will rapidly excrete the excess water through urine to protect your cells from swelling. In this scenario, despite drinking copious amounts of water, your cells remain unhydrated because the fluid lacked the necessary mineral escort to be effectively absorbed and retained. The master conductors of this intricate fluid dynamic are the kidneys. These two bean-shaped organs are sophisticated filtration plants, processing roughly 180 liters of blood every single day. Their primary function is not just making urine, but meticulously regulating our internal chemical environment. As blood passes through the microscopic filters in the kidneys, known as nephrons, the body continuously senses the concentration of sodium, potassium, and overall fluid volume. If you are dehydrated, the brain signals the release of antidiuretic hormone, prompting the kidneys to reabsorb water back into the bloodstream. Simultaneously, if sodium levels drop, the adrenal glands release a hormone called aldosterone, which commands the kidneys to retain sodium and excrete potassium. This dynamic, moment-to-moment adjustment ensures that our blood pressure remains stable and our cells bathe in the perfect osmotic environment. The kidneys demonstrate why the simplistic idea of hydration fails to capture biological reality. They do not just manage water, they manage the precise ratio of water to dissolved minerals, working tirelessly to preserve homeostasis against the fluctuating demands of our environment and diet. To truly appreciate this system, we must examine the specific roles of the major electrolytes, starting with sodium. Sodium has been heavily stigmatized in modern dietary discourse, often solely blamed for hypertension. While chronic overconsumption of sodium in highly processed foods is a valid public health concern, sodium itself is absolutely indispensable for survival. It is the primary electrolyte found in the extracellular fluid. It regulates total body water, maintains blood volume, and initiates the electrical impulses in nerve and muscle cells. Without adequate sodium, blood volume drops, leading to fatigue, dizziness, and impaired cognitive function. Working in constant tandem with sodium is potassium, the king of the intracellular fluid. While sodium dominates the outside of the cell, potassium dominates the inside. The concentration gradient between these two minerals creates the electrical potential across the cell membrane. This is maintained by a biological mechanism called the sodium-potassium pump, a protein complex that continuously moves sodium out of the cell and potassium back in, burning a significant portion of our daily cellular energy in the process. Potassium is crucial for regulating heart rhythm, facilitating muscle relaxation, and mitigating the blood pressure-raising effects of sodium. Studies show that a diet rich in potassium, primarily sourced from whole plant foods, is profoundly protective of cardiovascular health. Then we have magnesium, a mineral that often flies under the radar, but is a critical cofactor in over 300 enzymatic reactions within the human body. Magnesium is essential for the synthesis of adenosine triphosphate, commonly known as ATP, which is the primary energy currency of our cells. It also plays a vital role in regulating the channels that allow calcium and potassium to move in and out of cells. When magnesium levels are deficient, the entire electrolyte network becomes compromised, often manifesting as muscle cramps, irregular heartbeats, and profound fatigue. Let us look back at a pivotal moment in medical history that illuminated these mechanisms. In the mid-19th century, during devastating cholera outbreaks, physicians observed patients dying not from the bacteria itself, but from massive, rapid fluid loss. Early attempts to inject pure water directly into the veins of these patients proved disastrous, often accelerating cellular damage. It was the crucial discovery that injecting a solution of water and specific concentrations of sodium chloride, what we now call normal saline, could miraculously revive patients on the brink of death. This historical breakthrough provided undeniable proof that blood volume and cellular integrity depend entirely on the presence of electrolytes. It shifted the medical paradigm, proving that water without its mineral partners is biologically inert at best and actively harmful at worst when introduced directly into the systemic circulation. The delicate nature of this balance becomes acutely apparent during periods of intense physical exertion or extreme heat. When we sweat, we do not just lose water. We lose a significant amount of sodium, along with smaller amounts of potassium and magnesium. If an athlete or an individual working in high temperatures attempts to rehydrate solely by drinking massive volumes of plain water, they risk a dangerous condition known as hyponatremia. Hyponatremia occurs when the concentration of sodium in the blood becomes abnormally low. Because the blood is now heavily diluted, water rapidly moves via osmosis into the body's cells, causing them to swell. When this swelling occurs in the brain, it can lead to confusion, seizures, and in severe cases, it can be fatal. This stark reality underscores why sports science has shifted dramatically over the past few decades. Research indicates that replacing lost fluid is only half the battle. We must also replace the lost electrolytes to maintain the osmotic pressure required for cellular function. This is why medical professionals and sports dietitians emphasize electrolyte-replenished fluids during prolonged, heavy sweating. Understanding the science of electrolytes also requires examining the concept of bioavailability. Bioavailability refers to the proportion of a nutrient that is absorbed from the digestive tract and becomes available for use or storage in the body. Not all sources of minerals are created equal. The magnesium found naturally in leafy green vegetables, bound to organic compounds, is highly bioavailable. Our digestive systems have evolved to efficiently extract and utilize these minerals from whole food matrices. Conversely, some inorganic mineral salts found in poorly formulated supplements may pass through the digestive tract largely unabsorbed, drawing water into the intestines and causing digestive distress rather than contributing to cellular hydration. The gut microbiome, the complex community of trillions of microorganisms residing in our digestive tract, also plays a fascinating emerging role in how we absorb certain minerals, further highlighting that nutrition is a deeply interconnected systemic process. The scientific literature clearly demonstrates that hydration is not a static state achieved by hitting a daily water quota. It is a dynamic, continuous physiological negotiation. It involves the precise intake of fluids, the adequate consumption of bioavailable minerals from a nutrient-dense diet, and the flawless execution of renal filtration by the kidneys. When we look beyond the marketing slogans of bottled water companies and delve into human physiology, we find a system of breathtaking elegance and complexity. We see that water is the vital solvent of life, but electrolytes are the directors, guiding that water to where it is needed most, maintaining the structural integrity of our cells, and sparking the electrical impulses that drive our existence. By discarding outdated myths, we empower ourselves to make dietary choices grounded in biological reality. We learn to listen to our bodies, recognizing that the craving for salt after a long run is a physiological signal, not a dietary failure. We understand that eating a potassium-rich diet of fruits and vegetables is just as crucial for hydration as the water we drink. The science of cellular hydration reveals that optimal health is rarely about a single isolated nutrient or a rigid daily target. It is about understanding and supporting the intricate, interconnected mechanisms that sustain human life. Through this lens, the simple act of taking a drink transforms into a profound appreciation for the invisible, electrical symphony playing out within every cell of our bodies.